Hi everyone, welcome to Unit 22 of online course on probability distributions. In the last session, we have defined geometric random variable, its distribution function and mean, variance and some properties of the distribution. Now, we are going to discuss some more important properties and characterization results of geometric distribution. So, in this session, first we are going to derive the probability generating function. If x is a geometric random variable with a probability mass function f x is equal to q power x into p, where x is equal to 0, 1, 2, etc., then the generating function, probability generating function is given by p x s is equal to p divided by 1 minus q s. How this probability generating function is deriving? So, I will explain the method of derivation of the probability generating function. You are given x is a geometric random variable with a parameter p, suppose, and the f of x value is equal to q power x to p, where x is equal to 0, 1, 2, etc., and p plus q is equal to 1. So, this is the probability mass function of the geometric random variable with the parameter p. And our problem is to find the probability generating function. Probability generating function of geometric random variable. And probability generating function denoted by, let it be p of p x s. That is the probability generating function, and that is defined as expectation of s power x, whereas is a real number, real valued quantity. So, probability generating function p x s is equal to expectation of s power x, and that is equal to, by definition of expectation, this is equal to sigma over x s power x into f x. So, probability generative function is obtained by summation over x s power x f of x. For the geometric random variable, it is obtained by, this is equal to summation over x is equal to 0 to infinity s power x q power x into p, and that is sum over x is equal to 0 to infinity q s power x and p is taken outside, or that is same as p into 1 plus q s plus q s the whole square plus etc., or that is p into 1 minus q s, provided this q s is a modulus of q s is less than 1, because then only that is convergent. So, that this is equal to, and this is equal to p divided by 1 minus q s. So, probability generating function of the geometric random variable is equal to p divided by 1 minus q s, and that is the function of the geometric random variable which is generating probabilities of the geometric random variable. And similar to this probability generating function, we are deriving the moment generating function also. What is a moment generating function of the random variable? again if x is a geometry random variable with the parameter p, then probability mass function we know, and we are going to find the moment generative function. How it is obtained? The moment generative function, you are given x is a geometric random variable with the parameter p. So, f of x, we can have the value of f of x as q power x into p, where x is equal to 0, 1, 2, etc. And our aim is to find the moment generative function of the random variable mxt. Moment generative function is equal to, our definition is expectation of e power tx. That is our moment generative function. So, for a random variable, we are finding the moment generative function, and that is nothing but expectation of e power tx. And since it is a discrete random variable, the formula or the way in which the expectation is obtained by sum over x e power tx into fx. And substitute the probability mass function here. So, x is equal to 0 to infinity e power tx into f of x. We have f of x value q power x into p. So, that is the moment generative function of the geometric random variable. And to get the value, we are simplifying that expression, that is equal to sigma over x is equal to 0 to infinity. Again, p is taken outside the summation sign, e power tx and q power x are combined. So, we can write q into e power t all power x. Sum over x is equal to 0 to infinity q e power t all power x, or that is p into 1 plus q e power t plus q e power t all square plus etc. So, that is a non-infinite series, and the value is equal to p into 1 minus q e power t, provided this infinite series is convergent. That is modulus a q e power t is less than 1. So, this is power minus 1. So, this is equal to p divided by 1 minus q e power t. So, moment generative function of the geometric random variable is given by mxt is equal to p divided by 1 minus q e power t. And what is the cumulative generative function? For a geometric random variable, the cumulative generative function, that is a function which is generating cumulants of the random variable, is obtained by kappa xt is equal to logarithm of mxt. Earlier we have the moment generative function we have derived as p divided by 1 minus q e power t. So, that using that moment generative function value, we are deriving the cumulative generative function. And cumulative generative function is, by definition, it is logarithm of mxt, and that is equal to logarithm of p divided by 1 minus q e power t. And how from this cumulative generative function, how we can find the cumulants, that is explained as follows. How to find cumulants? Using cumulative generative function, we can find the cumulants as for the geometric random variable as follows. Already we have the value of the moment generative function we derived as p divided by 1 minus q e power t we have. So, you take the logarithm of that moment generative function, log mxt is equal to logarithm of this function, the value p divided by 1 minus q e power t. So, that is the cumulative generative function. and that value is, now we are changing that value, logarithm of mxt is equal to logarithm of p divided by 1 minus q e power t is p divided by, instead of this 1, we know p plus q is equal to 1. So, instead of this 1, let me write p plus q minus q e power t. What is the advantage of writing the Coulomb generative function like this? Because we can have this value logarithm of, this is p is cancelling from the numerator and denominator, we can have the 1, and this is again 1, q divided by p minus q divided by p e power t. So, Coulomb generative function is logarithm of 1 divided by 1 plus q divided by p minus q divided by p e power t, and that can be written in another form as logarithm of 1 divided by 1 minus q divided by p e power t minus 1. Earlier we have the 1 divided by 1 plus q divided by p minus q divided by p e power t. What we are doing? You are taking q divided by p out, common factor. So, this is e power t minus 1 you can write. So, we can write logarithm of 1 divided by 1 minus q divided by p e power t minus 1. Again, that is logarithm of 1 divided by a factor, that is equal to minus logarithm of 1 minus q divided by p e power t minus 1. So, Coulomb generative function of the geometry random variable is equal to minus logarithm of 1 minus q divided by p e power t minus 1. And now our aim is to expand this function. In order to expand this Coulomb generative function, use the logarithm of 1 minus x expansion. You know logarithm of 1 minus x, the expansion of logarithm of 1 minus x you have. So, that is using the logarithm of, logarithm of 1 minus x, and especially minus logarithm of 1 minus x we have. This is equal to x plus x square by 2 plus x cubed by 3 plus etc. On the basis of that expansion, we have logarithm of minus logarithm of, this is our x. This expression is treated as our x. So, minus logarithm of 1 minus x is expanded as x, that is, this is our x, that is q divided by p t plus t square by 2 factorial plus t power 3 divided by 3 factorial plus etc. That is our x. Then second factor is x square by 2, that is this x square by 2. So, plus x cubed by 3 plus etc. Remember, this whole factor we termed as x, and apply the expansion of logarithm of 1 minus x or expansion of minus logarithm of 1 minus x, then you will get the Coulomb generative function as q divided by p t plus t square by 2 factorial t power 3 divided by 3 factorial plus etc. Then x square, that is this factor all square divided by 2 plus the factor power 3 divided by 3 plus etc. So, the Coulomb generative function, we have the Coulomb generative function, this one minus logarithm of 1 minus q divided by p e power t minus 1, that is expanded, and we obtain this expression. So, once again you just look, earlier we have the Coulomb generative function as minus logarithm of 1 minus q divided by p e power t minus 1, and that is expanded, you will get the value as q divided by p t plus t square by 2 factorial plus t power 3 divided by 3 factorial plus etc. plus q divided by p into t plus t square by 2 factorial plus t power 3 divided by 3 factorial plus etc. the whole square divided by 2 plus then the remaining factors x cubed by 3 plus x power 4 by 4 plus etc. what is the advantage of this expansion? From this expansion, you can identify what is the coefficient of t power r divided by r factorial, because when you are identifying the coefficient of t power r divided by r factorial, we will have the cumulants. So, what is our first cumulant? Kappa 1. Kappa 1 is the coefficient of t power 1 divided by 1 factorial. Just look the expansion. What is the coefficient of t power 1 divided by 1 factorial? This is the coefficient of t power 1 divided by 1 factorial. All other terms are either t square, t cubed or higher powers of t. So, only the factor consisting of t power 1 divided by 1 factorial is this q by p into t. So, coefficient of t power 1 divided by 1 factorial is our kappa 1, that is our q divided by p. And what is the coefficient of t square divided by 2 factorial? See, the coefficient of t square by 2 factorial from the first expression, this is our t square divided by 2 factorial. So, the coefficient is this one q divided by p. And just look the second factor. Second factor, it is q divided by p t, this is squaring. So, this is our squaring term. So, that means q divided by p the all square and t square divided by 2 factorial, plus all other terms are now higher powers of t higher than t square. So, the coefficient of t square divided by 2 factorial is same as q divided by p plus q divided by p the whole square, and that is equal to p square qp plus q square, or that is q into p plus q divided by p square, or that is q divided by p square. So, coefficient of t square divided by 2 factorial from this expansion. Let me repeat once again, the coefficient of t square divided by 2 factorial we are identifying from the first expression, the coefficient of t square divided by 2 factorial is q divided by p. So, this is the value, and the second bracket you consider, that is squaring term. So, when you are squaring, this expression is t square, and so q divided by p the whole square t square divided by 2 factorial, that is 2 itself. So, the coefficient is q divided by p the whole square. All other terms are powers of t higher than t square. So, the coefficient of t square divided by 2 factorial is this one. Simplifying, you will get the value q divided by p square. What is the meaning? The second cumulant, that is the coefficient of t square divided by 2 factorial is equal to q divided by p square for the geometric random variable. So, we have comparing the coefficient of t power r divided by r factorial from the last expression, we will have the cumulants, especially first cumulant and second cumulant. Similarly, you can find the third cumulant, fourth cumulant, etc. by simplifying the expression, earlier expression, that is a power series of t, then you will get the other cumulants also. So, this is the way we are calculating the cumulants of the geometric distribution. And suppose our aim is to find the mean and variance of geometric distribution using moment generative function, that also possible. Instead of finding the mean and variance using the usual mechanism or usual technique of finding expectation of x and expectation of x square using the formula using the f of x value. Instead of that, suppose we are using the moment generative function, and we can find the mean and other moments using the moment generative function by differentiating the moment generative function. Just look here, what is the, suppose you have the geometric random variable, and what is the moment generative function we have discussed. X is a geometric random variable, suppose geometric with p, mxt we have derived the mxt already, that is the moment generative function, that is p divided by 1 minus q e power t. That is our moment generative function. And what we are doing? We are differentiating the moment generative function with respect to t. So, that means dmxt divided by dt we are finding, that is we are finding the derivative of this function, that is derivative of p divided by 1 minus q e power t with respect to t. And when we are differentiating this function using the quotient rule of the derivative, this is equal to see 1 minus q e power t into derivative of p. Derivative of p is, it is a constant, so 0, minus p and derivative of 1 minus q e power t. Derivative of 1 minus q e power t is 1 minus q e power t is differentiating, the derivative is minus q e power t. So, derivative of the factor 1 minus q e power t is minus q e power t divided by v square, that is the 1 minus q e power t the whole square. So, this is the first derivative, and what we are doing? We are substituting or make the t value as 0. So, put t is equal to 0 in this expression, the value is equal to, already this factor becomes 0, already this is 0. So, p q minus q e power t is e power 0, 1 minus q e power 0 the whole square, or that is p q divided by 1 minus q the whole square, or that is p q divided by p square, or that is q divided by p. So, already we have obtained the value of the mean by the usual technique. Now, it is the way in which we are calculating the mean value using the moment generative function, and using the moment generative function, the technique of finding mean or the other arbitrary moments are differentiating the moment generative function with respect to t and put t is equal to 0. That is one of the ways of finding the arbitrary moments. Or you can expand the moment generative function and find the coefficient of t power r divided by r factorial from the expansion. If it is possible to expand the moment generative function, then also that is another way of finding arbitrary moments. But for the geometric random variable, the convenient method of finding the moments using the moment generative function is using the differentiation technique. So, using the differentiation technique, the moment generative function is differentiating and put t is equal to 0, we have the expectation of x, this is our expectation of x is equal to derivative of mxt with respect to t and put t is equal to 0, that is q divided by p. Similarly, you can find the expectation of x square also. Expectation of x square, how it is obtained? Expectation of x square is equal to, you find the second derivative of the moment generative function and put t is equal to 0. Already we have the first derivative, already we calculate the first derivative. See, this is the first derivative, 1 p q, the first derivative is actually p q e power t divided by 1 minus q e power t, the whole square is our first derivative. So, you differentiate this factor, you will get the second derivative, that is the second derivative is equal to d by dt of p q e power t divided by 1 minus q e power t the whole square, and that is differentiating, you will get the answer, this is equal to 1 minus q e power t the whole square into the derivative of p q e power t. So, p q e power t is our the derivative minus p q e power t into 2 into 1 minus q e power t into minus q e power t, the whole divided by 1 minus q e power t the whole power 4. So, that is the derivative of the second derivative of the moment generative function, and here you put t is equal to 0, when t is equal to 0, when t is equal to 0, you can see this is this value is 1 minus q e power 0, that is 1. So, 1 minus q the whole square p q e power 0, that is 1, minus p q into e power 0, that is 1. So, 2 1 minus q e power 0 again minus q e power 0. So, this is plus divided by 1 minus q e power 4. So, that is the second derivative of the moment generative function when t is equal to 0. Simplifying this value, you will get, so p square, that is p cubed q, 1 minus q the whole square means p cubed p q plus 2 p square q square divided by p power 4. So, that is the, so when we are simplifying this expression, we have p, this is p square into p q, that is p cubed into q plus 2 p q, this is p, so 2 p square and this is q square, this q square divided by p power 4, or that is, see, p square q into p plus 2 q, so divided by p power 4. Again this is equal to p square q into p plus 2q can be written as p plus q, that divided by p power 4, or that is equal to q into 1 plus q divided by p square, or q divided by p square plus q square divided by p square. So, what is the result? The expectation of x square is equal to q divided by p square plus q square divided by p square. So, even though the way in which we are calculating the expectation of x square using the moment generative function, the only problem is to find the derivative of that function, very simple to find the derivative, and after getting the derivative, you just put t is equal to 0 in expectation of x. We have the first derivative of the moment generative function when t is equal to 0. Second, when you are finding the second derivative, we have the expectation of x square, and this even though this seems to be very lengthy expression, this is very simple to identify the derivative and put t is equal to 0 and simplifying, you get the result expectation of x square is equal to this value. Expectation of x square is equal to q divided by p square plus q square divided by p square. So, this is the way in which we are finding arbitrary moments, especially mean and expectation of x square. From this expectation of x square, it is possible to find the variance, as I already mentioned, variance is equal to q by p square, that is obtained from this expression by subtracting expectation of x the whole square. So, these are the some values with regard to generating functions, that is, first we discuss the probability generative function, then we obtain the moment generative function, and on the basis of the moment generative function we derive the expression for or expansion of the combinant generative function, and using the combinant generative function we obtain the covariance, and using the moment generative function we derived how we are in a position to calculate the mean and other arbitrary moments based on the moment generative function. These are the properties and these are the results with regard to generating functions of the geometric random variable. With this, let me wind up this session, and more properties and problems related with the geometric distribution will be discussed in the next module. Thank you.